Hello everyone. So this lesson is a basic extension of the logic that we learned about in the last video applied to computing. What we're going to learn about are these things called logic gates. The basic gist is in some sort of electronic device you're going to have, it's like some signal of electricity going through a circuit. It arrives at a gate and it'll change the current or output of that circuit depending on some of the conditions that it's meeting. So let's start with the simplest example, the NOT gate or the inverter. It has this triangle like shape with the circle in the front. It accepts a single input and outputs its opposite value. So if your input is 0, then it'll shoot out an output of 1. And in computing, 0 corresponds to the logical false and 1 corresponds to logical true. Keep that in mind. Or sometimes, like, there's many different analogs, like usually 0 is like 0 volts of electricity and 1 is like, I don't know, some other current, that's actually on. Anyway, if your input is 1, your output would be 0 because it's inverting the value. And since the values are binary or discrete, they only have 2 different choices, 1 or 0. It seems like a trivial operation, but in computers, we build these very highly sophisticated systems with this. Continuing onward, we have the AND gate. It's got this flat part on the left and then curves around along the right. The AND gate is just like the logical AND. It accepts 2 different wires, and if both of them are on, the output will be 1. If either of the wires are off, representing the 0, then your output will remain 0 or off. So, what would this give us? What signal? Well, since it's an and one of the currents is off, they both have to be true to be on, so your output would be off. It would not send a signal through there. AND is a Boolean operation, an operation that takes values that are either true or false and outputs them as true or false based on a logical manipulation of those inputs. In logic gates, 1 is true and 0 is false. We have this truth table, just like we did in the last video, that here's how you would convert it into zeros and ones for digital technology. True, 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 1, 1, 1, true, false, false, 1, 0, 0, so on. Yeah, we get the basic gist, right? Now, we have the OR gate, which accepts 2 inputs, and as long as either of those inputs is a 1, then it outputs a 1. And you notice it has this curved part on the left and then curvature going forward on the right. Each of these gates has a distinct sort of a symbolic shape to it. The logic gates are just abstract representations of real devices. A logic gate describes any device which can take in values of 0 or 1 and output a 0 or 1 according to its truth table. In most modern computers, logic gates are built using transistors combined with other electronic components like resistors or diodes. They're all wired together to make sure that they transform the inputs in exactly the way we'd expect. Here is just a basic circuit board. Obviously very enlarged. In real life, the circuits on your computer are microscopic. There's billions of logic gates in every computer. This is just a physical representation. You have your AND gate on the left and the OR gate on the right. Where here are the switches representing the signals going on or off. And computers will chain logic gates together to a series of them by taking the output from one gate and using it as the input in another gate. This is called a logic circuit. Circuits enable computers to do very complex operations that they could accomplish more than they could accomplish than just with a single gate. So here's a circuit. The smallest circuit is a chain of two different logic gates, so something like this, where inputs A and B go through the AND gate, and then the output of that gate goes through the OR gate combined with a third input C. So let's say my output was a 1. What would my A, B, and C values be? Well, if C was a 1, then no matter what, it'll always produce a 1. That's fine. But what if C was a 0? How can I make A and B produce that output of 1? Well, since it's an AND gate, they would both have to be 1 in order to produce the output of a 1, so that we have 1, 0 going through to get an output of 1. If any of A and B were 0, the AND gate would produce a 0 as an output. So if B was a 0, then the output of the AND gate would be a 0. And in order for us to have a total output of 1, the C would have to be a 1 as well. Moving on, we have this circuit that takes two inputs, sending them each through a NOT gate, then sends those outputs through an OR gate. This circuit is logically equivalent to what is called the NAND gate. It's a fairly common gate in computers. So let's see, if both inputs are 0, well then they would go through the NOT gate and become a 1 each, and then therefore we would have an output of 1. Well, what if we had A is 0 and B is 1? A would go through the NOT gate, become a 1. B would go through the NOT gate, become 0, but since it's an OR gate, we would still have a 1. Then, if A was 1, B was 0, well, we have a similar setup where 0 and 1 go through the OR gate to give us a 1. However, if both A and B were 1, they would go through the NOT gate as 0 and 0 and give us an output of 0. So we can see it's called the NOT, or the NAND gate, or the NOT AND gate, because it's the exact reversal of values that you would expect from a AND gate. Now, continuing onward, this one has two OR gates. A, B, C, D go through each of their respective gates, and then they go through a third OR gate. If the final output is 0, what is a possible state of the inputs? Whoops. Well, the OR gates can only be 0 if both the inputs are 0. So we have that will give us a 0 on the output. Similarly, this will give us a 0 on that output, and then we are given 0. So A equals 0, B equals 0, C equals 0, D equals 0. That's a combination. Does anything else work? Well, let's say I have 0, 0, 1, 0. There's just there's 1, 1 in there, right? The first one becomes 0, but the second gate is an OR gate, so we have an output of 1. And then since this one's an OR gate, it would not be a 0, it would be a 1. So it seems that this right here is the only combination that works. Then we have a similar setup, but now there's an AND gate. If your final output is 1, what's your different states for A, B, C, and D? Okay. So we have a comp for A, B, C, D, and then, well, we already know the final output's 1. Whatever. All right, A, B, C, D. All right, let's think about this. What if they were all 1s? So 1, 1, 1, 1. I think that would work because it would go through each OR gate as a 1, and then we would get a 1 as output on the AND gate. So what our real goal is, we need both of these to be a 1. Well, what combinations of A, B, C, and D would get us there? Well, as long as we have a 1 on each of them, it'll work. So 1, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, so on and so on. There's a lot of different combinations. 1, 0, 0, 1, 0, 1, 1, 1, and there's probably a couple more missing, but that is the basic gist of how these logic gates work.